huge. Listen to the science. Science is everywhere.
Welcome to Science is Everywhere. Today we're going to be talking about physics and skateboarding. Are skateboarders physicists? Most people would say no, but the physics of how they manipulate their skateboards is enough to make most undergraduate physics students scratch their head. Somehow academically untrained athletes can produce these complicated physical motions, but how could a physicist and a skateboarder have a conversation? Let's break down the basics of what's going involved with skateboarding tricks from a physics perspective and see if we can get that conversation started. We're going to be talking about vectors, energy, momentum, 3D space and degrees of freedom, and rigid bodies, center of mass, and hopefully Euler equations and Euler angles. Alright, so when we're doing math in 3 dimensions and we're trying to describe positions of things, it's going to be really complicated because every single position is going to have 3 different vectors that add up to it, x, y, and z in 3D space. So every single point has 3 additional points that basically describe where it is and how it's pointing. So we like to use vectors to simplify this. So every set of 3 points becomes one vector. So if you were trying to describe, I don't know, like an explosion or something, you'd have all of these little different points and they'd all have 3 different positions. So let's take that cloud of points and vectors and make it one single entity. See, this is a lot easier. We can just plot 3D vectors and save ourselves a lot of effort of trying to represent it with all of those different 3D coordinates. So like I alluded to earlier, vectors are important because they can be added together. So say we have, this resultant vector, that's what we call the product of it. It's orange, and it's going to the right. Well, we need to add these 2 other vectors that are black. One would have to go up y, and one would have to go to the right y. So say you wanted a vector that goes down to the left. Well, you need one to go negative x and one to go negative y. Now, vectors can add, and that's important because say we have a vector representing position or momentum. Well, those can be added together, and the result is a combination of the 2. So if you had someone doing a backflip, for example, and you shove them, you get translational plus rotational vectors. Overall, vectors are useful because they help us describe the direction of value in 3D or 2D space, and they simplify describing the coordinates and direction of one or many values. We also use vectors because they can be added and multiplied, so we might use them to represent things like position, momentum, velocity, etc. Thing is though, our vectors aren't going to always be represented in Cartesian coordinates. We might be in cylindrical or spherical space. So Cartesian coordinates, is just down, left, right, up, x, y, and z, what you're familiar with. Cylindrical coordinates has distance rho, that's the red arrow. It twists around phi and it goes up z. Spherical coordinates has a rho, think of a plane, that's their distance rho, and it can tilt in theta, left or right, yaw, or pitch, phi, up and down. Now that we understand vectors better, let's start talking about how things move through 3D space. So every object has a center of mass. It's usually near the physical center, and the whole thing moves around this center of mass, and forces act on the center of mass. Also, when we're talking about things in 3D space, we need to choose the same coordinate system to make sure we're all talking about the same thing. Normally, we're going to choose x, y, and z Cartesian coordinates, but not always. And that's important, because when we're talking about spinning stuff, we don't. So the degrees of freedom are the various ways the board can twist, turn, or spin. And that's also really important, and we're going to talk about that later. Because, there's different abilities to spin in one direction versus the other, some take more energy. But anyways, so we have the skateboard, we can visualize here, and it can roll translationally forward or backwards, and that would be in the x direction. At least we're going to call that x. Then you can go side to side, if you're turning or something. That would be the y direction. And then jumping would be z. Now you can also rotate the board, so about x would be a kickflip or heel flip, and about y would be, when you're ollie or something and the board's tipping. And then you can rotate it about z, which would be any type of spinning trick, like a pop shove it. So now we can roll and we can add these other rotations. So let's add in a trick like a pop shove it where you're rolling translationally and spinning about z. Okay, that's cool. Well, let's roll and spin about x and do a kickflip. Okay. Now we can also add in Z and X rotations and translational, like a tray flip. So we've established that vectors can be added, but now we've also seen that rotations can be added as well. So when we're considering the complex motion of a skateboard trick, like a 360 kickflip, we're going to have to translate between the rotation from the perspective of the skateboard. And when we do that, we're talking in Euler angles. So this is how the board is rotating from its perspective. And then we use these Euler angles to translate to Cartesian coordinates, which is the perspective of the ground. So I've explained how things move, but I didn't really tell you why. The answer is energy and momentum. Energy is a very specific quantity that can't be created or destroyed, only transferred between different types, so the total amount remains the same. Now the different types are kinetic energy, like things moving, rotational energy of things spinning, and potential energy are things of, fighting against gravity and they're above ground. So considering rotational energy, it takes a certain amount of energy to make something spin, and this is related to something called the moment of inertia. And the moment of inertia tensor, if we're talking about something that has 3 dimensions. So what's the moment of inertia? Well, the moment of inertia is basically how much angular momentum it takes to rotate something at a speed, and angular momentum is conserved. You know this because if you look at an ice skater while she's spinning, when she tucks her arms in, she spins faster. Now, no energy is created or destroyed. Angular momentum is conserved, so she spins faster when she changes her shape. And shape, therefore, is really important when we're talking about our moments of inertia. So all these different objects have different moments of inertia, and even different ones if they're moving about a different axis. Euler also gave us Euler-Lagrange equation, and it's basically Newton's second law for rotating objects. Basically, Euler recognized that rotating objects have energy and that it takes force to make something rotate. So he just equated the force with the motion that results. So speaking of motion, if we wanted to describe now the overall motion of a skateboard doing a trick, not from the perspective of the skateboard, we'd use these things called R vectors. And R vectors are composed of these different coordinates like we said before. But now we're concerned with forces and accelerations and velocities and all this stuff. And those are composed of derivatives of this R vector in spherical coordinates because we're talking about rotations and all kinds of twists and turns. So these derivatives of R vectors in spherical coordinates become super complicated because you have so many different ways that you can twist or turn. So in trying to understand the physics of skateboarding, we wound up talking about vectors, energy and momentum. We talked about Euler equations, all kinds of crazy stuff. Essentially, that was a upper level mechanics course in 3D rigid body kinematics. But I think we learned a lot of important stuff. So we know now what it looks like, for example, above, to just translationally move in x. And the speed in x would be the derivative of the x position. Now we can also add different things together. So we can move in z and we can move in x at the same time. And those vectors add up. Now we can also add rotations in either of our degrees of freedom, x, y, or z. So something can move forward in x and rotate in x. Now this is exactly the motion of a trick like a kickflip. Now we also talked a little bit about angular momentum, things spinning and turning, and the difficulty or moment of inertias, what makes it so something can rotate in different degrees. In different directions, and how this makes the motion harder and changes the way things rotate. And lastly, we talked about adding all of these things together, and a little bit about this, but I can expound more, that, the height of tricks is going to be constrained by the overall energy, because, like we said, energy is not created or destroyed. So if you want to do a trick, all of that energy has to also go into making the trick be as high as possible by fighting gravity. So you have to take all of your translational motion, how fast you're going, make the board spin by flicking it, and that creates a ton of rotational energy. And all of that energy that you gave to do your trick has to overcome gravity to make it as high as possible. So all of these really complicated things tie together. Basically, to sum this all up, we have a series of coordinates that are represented by vectors r, and when they rotate through 3D space in any direction, we use a spherical coordinate system that can rotate in theta and phi. We use Euler equations to explain how the forces and energy will connect to that resulting motion. Alright, I hope this was an informative video, and now you know a lot more about the physics of skateboarding than pretty much anyone else out there. So I don't know, could a physicist and a skateboarder have a conversation? I'm not sure, but hopefully we're a little closer to that happening. Thanks for watching, and stay tuned for more episodes of Science is Everywhere.
And we're on this planet, and Einstein's physics showed it, Max Planck's physics showed it, all. There's at least 12 dimensions. And now that's why all the top scientists and billionaires are coming out saying it's a false hologram. It is artificial. The computers are scanning it and